This is the second part of my talk about an introduction to radioactivity, and in it I'm going to talk about the interaction of a radiation with matter. In the first part of this talk, I explained the radioactive decay processes that lead to various emissions. We talked about alpha and beta emissions and gamma and X-rays. So we need to distinguish between the interaction of particles, which include alpha particles and beta particles, and the interaction of photons, gamma rays and X-rays, because they behave very differently when they interact with matter. So let's just think about different types of radiation. There are non-ionizing radiations, so called because they don't have enough energy to knock electrons out of atoms, so they can't ionize matter. Visible light, microwaves and radio waves all fall into this category of non-ionizing radiation, and they don't therefore cause any damage to biological tissues. On the other hand, ionizing radiations are those that do have enough energy to knock electrons out of atoms, causing them to be ionized. And the X-rays, gamma rays, beta particles and alpha particles that are products of radioactivity are ionizing radiation. They can therefore damage biological tissues, which leads to possibilities of causing cancer and genetic effects. And we need to realize that the radiation dose that these ionizing radiations deliver depends on how much energy is absorbed in tissues for each gram. So for radiation protection purposes, we need to know how we can block these radiations if they're coming from outside the body, so that we don't get any radiation dose from them. Or if the source is inside the body, we need to know how to allow the radiation to escape in order to keep the radiation dose down to a minimum. However, for detection purposes, we need to know how to maximize the chance of the radiation being absorbed in our detector so that we can detect it. So in talking about the interaction of radiation with matter, we need to take these things into consideration. I'm first of all going to talk about particle interactions. That covers alpha particles and beta particles. So let's see what happens when an alpha particle passes through some material. Now, an alpha particle consists of 2 protons and 2 neutrons. So it has 2 positive units of charge and a mass of 4 units. So when an alpha particle passes through the tissue, its electrical charge will easily knock electrons out of any of the atoms that it passes by, causing ionization and depositing energy in the material. But the alpha particle, being quite heavy, just carries on in a straight line regardless, causing ionization all the way. Now, if you think back to the model that I showed in the first part of this talk, demonstrating the atom in terms of a balloon with a speck of dust at the centre, you will remember that the atom is mostly empty space. So on that scale, the alpha particle will be like a speck of dust passing through a room of air filled with little specks of dust representing the atomic nuclei. So you'll realise that actually the chance of an alpha particle hitting a nucleus is very small, so mostly it carries straight on, and every now and again it does just hit the nucleus of an atom. The nucleus will recoil in this direction and the alpha particle will bounce off somewhere else, continuing to cause ionization. But because it's losing energy and slowing down all the time, it will eventually come to a stop after a distance we call the alpha particle range. So you see the electrical interaction with electrons in many atoms in the material cause dense ionization, so the alpha particle loses its energy very quickly and therefore has a very short range. In fact, the range of the alpha particle in air is a few millimeters, and in human tissue just a few microns. That means that if we've got a source of alpha particles outside the body, it's a very low risk, because any alpha particles that do hit the skin will be stopped in the superficial layers of the skin, which are dead anyway, and so it doesn't cause any harm. However, if we've got an alpha particle source inside the body, then we get a very high local dose, because all of the energy of the alpha particles is absorbed within a few microns within the cell in which the alpha particle originates. So we get a high amount of energy deposited per unit mass, a high dose. If we think about beta particles, the beta particle, an electron or a positron, a beta minus or a beta plus, is much lighter, and it only has 1 unit of charge. So an electron passing through some material will also cause ionization, but because it's so light, it's very easily deviated and undergoes a very zigzag path as it passes through matter. If it does happen to come close to the nucleus of an atom, it can be bent through a very large angle with a nuclear scattering, and in doing so, the acceleration that it produces sheds a X-ray called a Bremsstrahlung X-ray. That's the sort of X-ray that we get from X-ray tubes when an electron beam hits a target of metal. But because it's losing ionization, because it's losing energy by ionization all the time, the beta particle will eventually come to a stop after a definite range. It only produces a moderate amount of ionization, so it loses energy fairly quickly, but not as quickly as an alpha particle. And so it's got a short range, which in air is typically a few meters. So beta particles will pass across the one side of a room to another in the air, but in human tissue, the range is just a few millimeters. That means that if we got a source outside the body, then it can give a dose to the surface a few millimeters of the body. But if the source is inside the body, it gives a high local dose, not just to the local cells, but to the organ in which the source is concentrated, so anywhere within a few millimeters. Now we have to consider what happens with positrons, which is the anti-electron, because it's the antiparticle electron with the same mass, 511 keV, but an opposite charge. It has a positive charge instead of a negative charge. Now that means that positrons pass through tissue in the same way as the electrons. They produce ionization in exactly the same way as I've just shown you. But when they stop, they do behave differently, because they found themselves as positrons surrounded by material containing lots of ordinary electrons. So when a positron and an electron meet, they just annihilate each other, cancel each other out in charge, and the mass of both particles is converted purely to energy, according to E equals mc squared. So it produces 2 gamma rays, each with 511 keV of energy. So the process is that the positron will slow down and stop, meet an electron, and the two will annihilate, and we get 2 511 keV gamma rays coming off. So these gamma rays can each result in an additional dose, which we need to take into account, but in fact they're very useful in the technique of positron emission tomography, PET, when it comes to imaging positron emitters. Finally, let's talk about photon interaction. So I'm talking about X-rays and gamma rays, which are not particles but electromagnetic waves. So there are 2 processes we need to consider. The first of those is Compton scattering. Here a photon comes in and it passes through material, and instead of producing ionization, it can't produce ionization directly, it has no charge, it will every now and again interact with a free electron, one of the loosely bound electrons in the material. And if it does this, then it can scatter off in a different direction. We see here the gamma ray comes off there with lower energy, and the electron is knocked out, and the electron carries off some of the energy. So only some of the photon's energy is absorbed in this process, and if the scattering angle is fairly small, it will lead to a small amount of energy passed to the electron, and if a scattering angle is large, we end up with a high energy loss. Now this process becomes more important as the energy of the photon gets higher and higher, and it's also most important in low atomic number material, low Z, and human tissue has low atomic number, and so this is quite an important process in human tissues, particularly at higher energies. The other process we need to consider is photoelectric absorption. In this process, the photon comes in and it interacts with one of the bound electrons that are tightly bound within the atom, and it can knock the electron out completely, and the photon loses all its energy and passes all its energy onto the electron, which is known as a photoelectron. Now, if that knocks an electron out of the one of the bound electrons in an atom, that will inevitably leave a vacancy in that shell, and so higher energy electrons from higher shells will drop down, and that also results in the emission of characteristic X-rays. So the photoelectric absorption not only produces a photoelectron but also produces some X-rays as well. But in this case, all of the photon's energy is absorbed and it goes into the electron, and this becomes less important at high energies, but it's most important in high atomic number material. So this is most important in things like lead and less important in things like human tissue. So let's see what happens when gamma rays or X-rays pass through a block of material. If a gamma ray comes in, it may well pass straight through the material without interacting at all. The gamma ray has no charge, so it's not going to produce any ionization unless it interacts. It may undergo a photoelectric absorption, in which case the gamma ray gives up all its energy to an electron, and that electron goes on and deposits its energy within a few millimeters of that position. It may be that the gamma ray undergoes some Compton scattering, in which case it gives up some of its energy to an electron and carries on in a different direction after it's been scattered. In both of those cases, the electron that is produced is a secondary electron, and that's what produces the ionization and deposits the radiation dose in the material. The photon itself doesn't actually produce any ionization, it's only these secondary electrons. So if we imagine lots of gamma rays coming in, some may go straight through, some may interact at all. And we can't say that there's a definite range to stop them, but we can say that if, for example, we had 10 gamma rays coming in and only 5 come out, we have stopped half of them. So instead of talking about a range, we talk about the half value thickness, the amount of material that's needed to reduce the intensity by half. So we don't have a definite range for gamma rays and X-rays, it's just a gradual reduction in the intensity, and we can quantify that by the half value layer. So we have the situation of exponential attenuation, where the intensity of the radiation falls off exponentially with thickness of material, giving us a curve showing intensity of radiation against thickness falling like this. And we quantify that by the half value layer, which is the thickness required to reduce the intensity to 1/2 of its value. And we can write that mathematically as Ix, the intensity after a thickness of material x, is I0, which is the intensity initially at 0 thickness here, multiplied by E, which is a constant, to the power of minus 0.693 times x, the distance over the half value layer. So when x is equal to the half value layer, that is 1, so this is e to the minus 0.693, which turns out to be exactly a half. So we get Ix, the intensity, is equal to I0 times a half. So when we get to this point where we have come to 1/2 value layer here, the half value layer reduces the intensity to half the initial value. That's exactly the same as what we had with the equation for the decay of radioactivity with time that I talked about in the first part of this talk. So when x is equal to 2 half value layers, this is equal to the e to the minus 0.693 times 2, which falls to a quarter of A0. So after 2 half value layers, it's fallen to a quarter of A0, because that's half of what it was at the 1/2 value layer, and one more half value layer will halve it again, so it falls to 1/8 of I0, and so on. So it falls it falls all the time, but never quite gets to 0. So typically in tissue, the half-value layer for typical energy of gamma rays or X-rays is a few centimeters. So some photons will be absorbed and some will penetrate. In lead, the half-value layer is a few millimeters, so if you've got a reasonable thickness of lead, that will stop most X-ray or gamma ray photons, but not necessarily all of them. Notice that the half-value layer will increase with energy, so as the energy of the X-rays or the gamma rays goes up, you need increasing thicknesses of lead in order to stop it, but they will more easily penetrate out of human tissues. So let me summarize what we've said in this part of the talk. Alpha and beta radiations are particles, so they will lose their energy through lots of small interactions with the material, causing ionization along the way. That means that they easily stop and have a short range. So if we got a source outside the body, that's easy to shield, but bear in mind that if we're talking about positrons, then after they've stopped they will also produce 511 keV gamma rays by annihilation with an electron, and that may well be more penetrating than the original positrons. But if we got a source inside the body, that will inevitably deliver a local radiation dose, because the radiation will only travel a very short distance from the source. On the other hand, gamma rays and X-rays are electromagnetic waves, so they're not directly ionizing. They lose their energy through photoelectric absorption or Compton scattering, or possibly a Compton scatter followed by photoelectric absorption, so it's just one or two interactions. And it's the secondary electrons that they produce which produce the ionization. So the gamma rays and X-rays have no definite range. Instead, we talk about the exponential attenuation with a half-value layer. So if you want to shield against gamma rays and X-rays, you need lead shielding, which will give a large attenuation and can be very effective at shielding. But if we're talking about passing through human tissues, they can penetrate a few centimeters. So if we have radiation coming from outside, some of it will be absorbed in the patient. If we have it coming from inside, some of it will be absorbed and some will escape. So the radiation dose from gamma rays and X-rays is going to be distributed rather than local. So that's the end of the second part of this talk. In the third part, I'll discuss some of the radionuclides that are used in nuclear medicine.